Thank you for the invitation. And thanks for everybody that organized this meeting. This is actually gave me the opportunity for my first international meeting after the pandemic. So as you can see from my affiliation, I'm based in Shanghai, in China, at the University of Science and Technology. Unfortunately, I was really hard experimentally with my results there and setting up a new lab. So everything I'm going to talk today is actually from Vienna, from the Atom Institute, so all the results. So the new results are too new. And I basically, today I decided to talk about the latest results from there, which is a new resonator that we developed, which allowed them to do two experiments, the super radiance experiments, and actually measuring relaxation time of the NV center at really low temperatures. So as an introduction, we called our research hybrid quantum systems, and we're doing quantum optics with spin ensembles. So what we have is actually a diamond here with many spins. So it's not single spins, in contrast to what Eugene talked. So it's an ensemble, many spins of NV centers, and then we put it on a superconducting chip. So you might know these chips, we kind of pioneered these chips for superconducting qubits when I was a postdoc at Yale for circuit QED. So if you look at the chip from IBM or Google or Yale, these are kind of these chips with a kind of transmission line, coplanar waveguide resonator. And this is a very old-fashioned transmon qubit here. But there's no qubits here. So Eugene actually gave a really nice introduction to NV centers. I don't have to download it from Wikipedia, so I bring it to you. This is really like a diamonds model. That's also what you do when you don't have a lab and only a 3D printer. So it's a diamond lattice with a phase center cubic, and then basically the NV center is one of many defects, kind of just replacing one carbon side with nitrogen, and the white sphere is the hole. I'm certainly, Tuna will talk about the optical transitions. So usually you use optical transitions in the systems. I'm just, when I'm talking about photons, I'm just talking about the ground states, the 2.8 gigahertz splitting that we have heard before. And yeah, so photons for me has this kind of wavelength when I'm talking about photons. Okay. So this is an example of the old experiments. So we've done a whole series of experiments and putting actually diamonds on these kind of chips. This is an experiment where we actually coupled NV centers over really like centimeter distance. You can recognize the chip here with the coplanar waveguide starting here and then meandering underneath these two diamonds. The diamonds, they are black actually because they have a large concentration of NV centers. So we have really lots of NV centers. Now the problem with these experiments, they work fine, and for certain experiments it's all good. One problem is if you look, this coplanar waveguide structure was developed by electrical engineers to concentrate the fields or kind of shield the fields in these gaps. So the field is extremely high here in these gaps, but it decays very rapidly as it goes away. So it's concentrated, but if you put a diamond there, you have a lot of spins above here, and they couple really with long, let's say, with the coupling strength varies a lot with over orders of magnitude as you go across this diamond. So certain experiment, so for example, just putting a pulse in and flipping them upside down, polarizing the whole thing is impossible in a structure like that. So in Vienna, we came actually kind of by an accident up with this structure, and it looks like follows. So what you see here is kind of two flaps of a bow tie. This actually in the middle is the diamond. And then, then there's a cover going, a lid going over this structure. And the structure is super simple. It's just an LC resonator. So you have the capacitor basically being formed by these two, let's say, flaps and the lid. So you have a capacitance here and a capacitance here. And then the current, as you see, if it's oscillating, is running down these kind of pillars into the base and back here. And this creates a magnetic field, so it's an inductor. So we're going to, let's say, The nice thing about that, it's a very homogeneous field, so the strength doesn't vary a lot. We've done that in the machine shop in Vienna, and we reached with this structure in, let's say, clean copper, quality factor of 2000, completely explained by the residual resistance of the copper. So nothing matching here, or also nothing to improve. Sorry, it's not switching forward. Okay, you can see we cooled it down with a diamond, and you can see a really nice avoided crossing. And so this is kind of the resonator by itself in logarithmic scale. And then when we tune the NV centers, we see a really nice strong coupling on this. And as I said, the field distribution here, the field strength is extremely homogeneous. This is just a calculation, I have to say, but let's say the following experiments basically justify that we have a very homogeneous field. If you're interested, follow this paper. And as I said, this is really like 1% homogeneity, while we have here orders of magnitude changing in this kind of coplanar waveguide structure. What we also did is actually making these structures out of aluminum. This is not, let's say, maybe you should at one point try special aluminum. This was just the normal aluminum that I had lying around in the workshop. With that, we actually reached a Q of 500,000. That's at the single photon level. The disadvantage of that, I mean, it's an aluminum box, and we cannot apply a superconducting field because of the Meissner effect, obviously. But that's not a hopeless story. So what you can do is a so-called dispersive measurement. So for example, for this resonator, how we had it here, this had a frequency of 3 gigahertz, and then the spins without magnetic field are at 2.88 gigahertz. So basically we're in the regime where the detuning, so the difference between these two, is much larger than the coupling. And then I heard people telling me, okay, there's nothing to see there anymore. This is true to 0th order, but not to 1st order. So if you're a theorist, maybe you know this famous Jaynes-Cummings Hamiltonian. Sorry, that's Davis-Cummings with, let's say, many spins, where you create here a photon in the resonator and kill an excitation in an ensemble, or vice versa. And if you then, in this limit, the so-called dispersive limit, you arrive at this limit, or this Hamiltonian, where you have, basically you can read it like, this is the frequency of the resonator with A dagger R. And then you get an extra term. You see the small number, that's G on delta. That's a small number in our problem. So it's a small term, but it depends on actually the polarization of the spin. And the nice thing about this, it's the so-called quantum non-demolition measurement. It's used standard now for measuring superconducting qubits and things like that. I would rather call it the quantum least demolition measurement. But it's a really ideal quantum measurement for doing things because because this Hamiltonian commutes basically with your system. So what can you do? So we started out tackling a problem that's called superradiance. The idea is, this is actually a review paper from Serge Roche from the Nobel Prize. The idea of superradiance is if you have many spins and they decay, it's just spontaneous emission. However, if you bring the atoms within the wavelength, you have basically a self-triggered spontaneous emission. So the idea is one of the photons is trying to decay, and then all the others then feel this photon to be decaying, and so you get a stimulated emission. The prediction is actually, it starts out with an enhancement that is proportional to the number of spins at the equator here for the Bloch sphere is proportional to n squared, the number of spins squared. So that's the theoretical thing. Okay, so we've done the experiment. You can see the experiment here. This is time versus the signal that's coming out of our cavity. And let's look at that, for example, this trace here. So this is actually the pulse with which we flip the spins upside down. So they're all mostly in the excited state. So this is just, it's also coming out of the cavity. And then we see actually a very short burst of photons coming out. And our claim is actually that's the super radiance. And the idea is, but the problem is you have to prove that. And our proof was also depending on, let's say, our system made it possible that we can do that. We change actually here on this axis the number of spins. You see here n, 2n, 3n, 4n. And that's actually related to the diamond. So you can see these defects are randomly distributed over the diamond. But if you look at the diamond structure here, you only have 4 possible directions. And it's kind of, yeah, it's a single crystal that we use. And and there are just 4 possible directions. And now, because we have a 3D magnetic field, we can tune different NV centers or subensembles of this structure into resonance. So, for example, if we go along the crystallographic axis, 1, 0, 0, you tune them all the same. If you check, the angle is all the same with them, so you're basically at this position. Or what you can do along the 1, 1, 1 axis here, so you tune this axis much stronger. So this comes first through the resonator, and then these 3. So you can check 1 and 3. Or if you play in the plane, you can actually select 2 subensembles. Now, if you do that and check the height, the prediction here was this has to be, the intensity has to be proportional to n squared. We do that, and actually what we get out is a law n to the 1.5. Was a little bit first disappointed. The reason for that is that this is not 2, is we have inhomogeneous broadening. So this system has a lot of inhomogeneity. It's a solid state, huge solid state system, and it has homogeneity. We have done kind of quite simple, I mean, experimentalists doing theory, and we can predict this 1.5. But I should really emphasize, the important thing is it's actually not linear. So it's a really clearly nonlinear effect with a power 1.5 showing that is actually something nonlinear going on here. And that's basically what let us claim that it was super radiance. Okay, that brings me to the second experiment, and this allowed us to measure the relaxation time T1 property of the, let's say, NV center. So what we do is here, we do the experiment the following way. We start out at high temperature. Reminder, high temperature for us, the 2.88 gigahertz of the NV center, that's basically 145 millikelvin. So 2.7 is really hot for us. Basically meaning that all the spins are in a complete thermal distribution. We ramp down the magnetic field, the temperature. So we ramp it down here to a certain value. And then just watch by gamma 1, so the relaxation time, the spins going into the equilibrium. And thanks to the fact that we actually can make this dispersive measurement, we can really measure that, and observe it, because it's quantum non-demolition, we can just continuously observe this measurement. Okay, so we do that for different final time. So this is for final temperatures, sorry. And then watch the whole thing relax to the ground state. You can see, so these are exponential curves, and that's from this kind of exponential factor here, we determine T1 of the system. And please look at the time scale, this is really like hours. So it takes hours for the spin to relax. And we basically measure that for different samples, so there's a bunch of different samples. And you see that. And the most, let's say, the cleanest diamond like that took actually up to 8 hours to relax back to the ground state. So we were puzzled as an experimentalist, and then we went actually and tapped into the excellent knowledge that's available in Vienna. So there's a lot of people doing DFT in Vienna. We went to Peter Mohn, who's a specialist on that, developed a lot of these codes, and he helped us really find out what's going on. So with his PhD student, Johannes, where is he? I don't find Johannes Kugler. Johannes he did all the calculations and checked a lot of mechanisms that would do this relaxation. In the end, it's actually the simplest one, and it's just basically decaying into the now phononic bath. So it is for the NV center, it looks at a bunch of phonons, decouples to the, let's say, empty phonons if you're really at low temperatures, and decays there. And it kind of this temperature behavior that we see here is the change of spontaneous emission here if the phonon bath is empty, and then going up and being here, this linear increase is stimulated emission absorption of the whole thing. Okay, also then we discussed, and basically in the beginning we were definitely surprised about this long 8 hours time scale, but then all with the discussions with Peter Mon was the reason this takes so long is just that diamond is a super stiff material. So it is really hard and stiff, which basically means at low, let's say low, it is extremely low frequencies of phonons, there are no phonons available. So the phonon density is extremely low, and that's why it's so extremely long. Okay, this is an animation. Actually, that's really like a DFT calculation. So the light blue are the electron wave functions, and then exaggerated are the vibrations that basically take away the excitation of the NV center. Okay, with that, I'm at the end of my talk. I showed you these lumped element resonators, which allowed us to do these new experiments, the superradiance. And as I mentioned here, let's say what the important thing is really like this peak height scale actually non-linearly, so we can really claim superradiance and demonstrate it. And then the measurement of T1 of NV centers at really low temperatures, low being lower than the, let's say, transition frequency, like that. I'm not yet finished, so I'm now doing some shameless advertisement. And actually, as I said, so I moved to Shanghai. Oh, there's some picture missing. Sorry. Shanghai is an excellent superposition of East and West. These are actually pictures from the former French area. There used to be a picture of the English area, the British area. Despite all the, let's say, stereotypes, the air is actually really clean because we are right next to the sea. The reason, okay, sorry. The reason I actually went there was Chanwei Pan. So he founded this quantum institute. Our university is in Hefei, but we are in Shanghai. So Chanwei founded this really quantum institute. That's definitely one of the top quantum physics institute in the world. This is actually my apartment, and I look down here on this experiment. This is a tent where if there is no clouds, they move it back and take a telescope and actually receive from the quantum satellite photons and do all this quantum key distribution. This is the experiment from Chaoyang Lu, the kind of the photonic quantum computer. And the reason I went there is the superconducting quantum computer. This is an older picture with 62 qubits, superconducting qubits. That's why I went there. And basically, if you want to come, join us. We have everything available, projects, PhD, postdoc, if you want to join. That means if you need a professorship, you have to talk via me to John Wei, so he decides on that. I cannot decide. A good example is actually Victor Johannes from Spain. And he just got a Marie Curie fellowship, outgoing fellowship, going out of Europe, paid by the European Commission. And generally, if you want to come and visit us, we are now open. We have a lot of money from the last 3 years to host visitors. And with that, thank you very much for your attention.